Hey, North, Mr. Yurgler here. Let's talk about phase diagrams and heating curves. Just a few quick things on phase changes. Here's a great diagram kind of going from showing the differences between solid, liquid, and gas and the transitions between each of those phases. Ask yourself real quick, which of these phase changes, which transitions are exothermic? You may be tempted to say that vaporization is exothermic because it happens at a high temperature, but actually condensation is exothermic, along with deposition and freezing. Okay, so actually everything over here. When we're decreasing our energy, think of gas as a very high energy and solid as a very low energy by comparison. And if we think of our particle pictures, to go from a gas where you're flying around at high speeds and there's no intermolecular forces holding the molecules together, to go from that phase to a phase like this, you're actually going to decrease your energy. You're going to give off energy in the process, and giving off energy means it's exothermic. So endothermic is the opposite, right? Endothermic would be vaporization, sublimation, and what's sometimes referred to as fusion, which also just means melting. One thing to note too is that the heat of vaporization, the delta H is technically enthalpy, but sometimes we'll say just heat of vaporization and heat of fusion. The heat of vaporization is always greater than the heat of fusion. And from a particle picture perspective, that makes sense. To go from liquid to gas, we have to completely break those intermolecular forces, whereas to go from solid to liquid, you only have to kind of let them go enough so that they can kind of rotate and translate around each other. They don't have to completely separate. You're not separating the molecules completely to be independent from each other. If we have some gas particles and some of them happen to be moving relatively slow, they strike the surface, they could be grabbed, so to speak, by the molecules at the surface and kind of engage in those IMFs. Meanwhile, if you have some molecules at the surface that happen to be going relatively fast, they might have enough energy to suddenly break away from the IMFs and go make the transition from liquid to gas. Now imagine this container, this is kind of an open system as it's drawn here, but imagine this container is closed and we have this all kind of sealed off. Over time, if we continue to vaporize the liquid, we're gonna really populate this headspace here with vapor. And that vapor is going to exert more and more pressure the more and more molecules that make that transition. Eventually, we have so much force pushing down on the liquid, so many collisions here, that it actually gets more difficult to vaporize at the surface, and so it will vaporize underneath the surface. That's what's happening with boiling. We've increased the vapor pressure to match the atmospheric pressure is when it starts boiling, and it evaporates not only at the surface but also kind of throughout the liquid. And that's always going to be at a specific temperature. So the vapor pressure is dependent on particle size. The bigger the particle, the slower it's going to move, and the slower it's going to move, the less vapor you're going to have. The less vapor you're going to have, the less vapor pressure you're going to have. So in relation to temperature, the higher the temperature, the higher the vapor pressure, and the higher the molar mass, so that is another way of saying the particle size, the lower the vapor pressure, right? A large particle is going to have a really low vapor pressure. This is assuming we're keeping IMFs consistent. All right, let's take a look at these two curves. Which sample has the higher temperature and which sample has the higher vapor pressure? Pause the video for a second and think about that one. Pay attention to the axes on the graph. I really like using this simulation here. So this is what we would typically think of as how gases behave, kind of following kinetic molecular theory. So this is one gas, one sample of gas, so these are all the same type of particle, and we have a live distribution of the speed of the molecules. So we have some going slow and they are shown as blue, and then the faster they go, the temperature change or the color changes. Now it's easier to kind of keep track of what's going on when there's less molecules, but our curve is actually better the more molecules we have, right? So if I add a bunch of molecules, notice my curve kind of gets a little smoother and it follows the overall curve pretty well. Now if I heat this up, what do you expect to happen with this curve? Should it shift left? Should it shift right? Would it stay the same shifting but just get taller? What do you think would happen? Let's go ahead and add some heat. So if I turn this heater on, it's applying the heat here. Look at what's happening to the molecules. You can tell they're moving faster, but also look what is happening to the curve. Let me stop it there. The curve actually broadens out, and this, if you pay attention to what the curve is showing, this makes sense. We have more molecules going at a faster speed. We have relatively fewer molecules going at a slower speed on average, right? And so it doesn't get taller because the height is the number of particles, or the fraction of the particles that are going that particular speed or having that particular kinetic energy, right? The faster our particles are moving, the greater the distribution. So it would actually kind of smooth out and it would get longer. So when we go back to this, the B curve is actually at a higher temperature. And because it's at a higher temperature, you would have a higher vapor pressure with that one as well. In A, there's more molecules, a higher number of molecules moving at a slower speed. This is another way to represent it. This is showing activation energy, but we could treat this as like the threshold required to break the IMFs and go from liquid to gas, right? If this is the threshold in order to make that transition, then at a higher temperature, a higher portion of them are going to make that transition. At a low temperature, you'll still have some evaporating, but not very many. This is what's known as a heating and cooling curve. So it's a heating curve if you're going to the right, it's a cooling curve if you're going to the left. Remember that at the plateaus, there is no delta T, there's no temperature change, and so the heat, Q is heat, is just the mass times the heat of fusion or the heat of vaporization. And on the slopes, there is a change in temperature, and so the amount of energy is equal to the mass times the specific heat times that change in temperature. We're not going to get into these calculations just yet. We'll come back to that in the future. The main point here is that there's plateaus at the melting point and vaporization point. And that's due to, again, think of the particle picture, right? We have to absorb energy in order to break those bonds. And while we're absorbing energy to break those intermolecular forces, it's not going to increase the temperature. You won't increase the temperature until you've already separated the molecules. So any additional energy goes to breaking those IMFs. The plateaus are going to be at the melting point and freezing point for that particular substance. In this case, we're showing it for water, which is probably the most common example that we'll look at. But it is possible to have those plateaus at different temperatures, which means that the melting point is at a different temperature. Last diagram I want to look at is called a phase diagram. Phase diagram shows all three phases as a function of pressure and temperature. So at a given temperature and pressure, what phase would a given substance be? At 100 degrees Celsius and a pressure of 101 kilopascals, which is about atmospheric pressure, we're right on the line between liquid water and gas. Which makes sense because that's the boiling point of water. So the line represents an equilibrium between the two adjacent phases, right? If we decrease the pressure, like if you increase your altitude, your boiling point, your temperature also decreases, right? If we increase the pressure, like in a pressure cooker, the boiling point increases. The triple point is where we have all three phases existing in equilibrium. And for water, that'd be at a really low pressure and a really low temperature. We can also look at the phase diagram for carbon dioxide. This one's interesting because carbon dioxide sublimes. It goes straight from a solid to a gas at atmospheric pressure. You can make it melt, but you have to get it up above 5.1 atmospheres in pressure in order to get it to melt. So moving from solid to gas with carbon dioxide would be an endothermic process, right? Because we're absorbing energy to make that transition. To go from gas to solid would be the opposite. That would be exothermic. So it depends on which direction you're traveling from what phase to what phase. Phase diagrams aren't a major point in AP chemistry, but you may see them here or there, and so you need to be comfortable with kind of reading them and making sense of them. If you have any questions, make sure you write those down, and we'll get some practice with this in class. This is Mr. Yerler signing out.